So back in 1901, you have this brilliant physicist, Max Planck, and he's really just trying to fix a broken formula. That's it. He wasn't trying to start a revolution, but in fixing that one little problem, he accidentally stumbled upon the foundations of an entirely new reality, the quantum world.
So where does this whole thing kick off? Well, with a crisis. There's this theory, Wien's law, that Planck himself had actually championed, and for a while, it seemed to work beautifully for describing energy and radiation. But then, new, more precise experiments come out, and the data is just undeniable. In his own words, the law was not valid generally. I mean, can you imagine? The very foundation of your work just cracks?
Okay, so what was the problem exactly? Well, Wien's law was great for short wavelengths of energy. Think ultraviolet light. But the new data revealed that for longer wavelengths, like infrared, the theory just completely failed. It wasn't a small error. It was a huge, undeniable problem in physics that needed solving, and fast.
So this brings us to our first chapter, a broken law of physics. This is all about what happens when the data just looks you in the face and says, nope, you're wrong. Planck, being a very methodical physicist, had to confront it. The evidence was irrefutable. Something at the very core of physics had to be wrong.
And what's so fascinating is how systematic Planck was about this. He didn't just throw out the whole theory. No way. His goal was surgical. He was going to go back into the math and find the one specific term, the single faulty assumption that was causing the entire theory to break down.
And so, the hunt begins. Planck starts retracing his steps, really focusing in on the tricky relationship between energy and entropy. He tried tweaking his ideas about entropy, but nothing worked. He was cornered. And when you're cornered like that, you're forced to question something much, much more fundamental.
And this is the moment where everything changes. After hitting dead end after dead end, Planck is forced to consider an idea that went against pretty much all the physics of his time. What if energy isn't smooth? What if it doesn't flow like water, but instead it comes in distinct individual chunks?
Think of it this way. Classical physics saw energy as a smooth ramp, where any value is possible. You can be anywhere on that ramp. But Planck's radical idea was to see it as a staircase. You can be on the first step or the second, but you can never be in between the steps. Energy could only exist in specific, distinct amounts. Planck called these individual energy steps energy elements, and he used the Greek letter epsilon as their symbol. This was the fundamental building block. He proposed that the total energy in a system wasn't a continuous value, but an integer multiple of these tiny, indivisible packets.
Now, thinking of energy as individual packets was the key. It let Planck use statistics. It became a counting problem. If you have a certain number of resonators, those are the things that vibrate, and a certain number of energy packets to give them, how many ways can you distribute them? By counting all the possible arrangements, he could find the most probable state of the system, which was the key to unlocking the formula.
But here is the crucial point. Planck himself called this an act of desperation. He didn't have a deep physical reason for it. He didn't necessarily believe energy was truly chunky. He did it because it was the only mathematical trick that allowed him to get a result that could potentially match the data. For him, it was a purely formal assumption.
And this leads us to the heart of the discovery, this impossible, radical idea of quantizing energy. A mathematical trick born of desperation was about to unlock a new law of nature.
Then came the next brilliant leap. Planck realized the size of an energy packet, epsilon, wasn't fixed. It had to be proportional to its frequency, which he called nu. And to link them together, he introduced a completely new number into physics, a universal constant of proportionality he called h.
And with that, everything just clicked into place. The idea that energy comes in packets, combined with the idea that the size of those packets depends on their frequency, was the master key. It solved the entire puzzle.
And this is it, the trophy at the end of the hunt. Now, don't worry about all the symbols, just appreciate what this formula did. Derived from his act of desperation, this single equation perfectly described the data for all wavelengths from short to long. It was the complete solution. So Planck now had a correct and incredibly powerful new law, born from an assumption he barely believed himself. But the story doesn't end with a formula, because inside that strange new formula were two letters that weren't just mathematical placeholders. They were new, fundamental constants of nature. Numbers that described the very fabric of reality, which had been hiding in plain sight within the glow of hot objects. The first was h, which we now call Planck's constant. This tiny number defines the scale of the quantum world.
It's the fundamental constant that separates the smooth, continuous world we see from the chunky, quantized reality underneath. It is one of the most important numbers in all of science.
The second was K, now Boltzmann's constant. This is the number that connects the microscopic world of vibrating atoms to the macroscopic world we feel as temperature. Basically, it translates atomic jiggling into heat. And Planck's work gave us the most precise value for it yet.
And so, the legacy of Planck's paper wasn't just a corrected formula. It was the discovery of these two hidden numbers that govern our universe from the smallest particle to the largest star.
So let's bring it all together. It started with a simple, practical problem, a formula that didn't match the real-world data. Just a nagging inconsistency that needed a fix.
And that fix, that act of desperation, turned out to be the first, tentative, and almost accidental step into the strange and wonderful world of quantum mechanics, the theory that would define the 20th century and beyond.
And this leaves us with a fascinating thought. Planck overturned a law that seemed solid. It makes you wonder, doesn't it? What accepted laws of science today are just like Wien's law, mostly correct, but just waiting for one new piece of data and one radical idea to reveal a whole new universe underneath.